Hello everyone, and welcome back to AISC's Night School, Seismic Design in Steel, Concepts and Examples, written and presented by Raphael Sabelli of Walter P. Moore. Today is March 12th, 2018, and this is Session 4, Seismic Design of Buildings. My name is Brent Liu. I am with AISC's Continuing Education Group, and I'll be moderating today's presentation. Let's get started. I want to welcome back our speaker, Raphael Sabelli. Mr. Sabelli is the Director of Seismic Design with the San Francisco office of Walter P. Moore. Raphael has recognized expertise in seismic design and steel structures. His experience includes design of new structures, retrofit of existing buildings, nonlinear seismic analysis, and the development of new systems. He participates in several national committees responsible for code development, including several committees here at AISC. Welcome back, Raphael, and I'll hand things over to you.
Thank you, Brett. And welcome back, everybody, as we recommence our 8-week night school on seismic design. I won't go over the objectives again. Hopefully we're making progress towards them, and we are in the last session of our general issues related to seismic design before we begin our example. As usual, I'll direct you to the Seismic Design Manual, Ductile Design of Steel Structures, and Earthquakes and Seismic Design publications if you want to read further, and we have some additional publications mentioned at the end of this session. We also have the Solution Center and Night School and myself to answer your questions. So we've been through some of the basics of seismic design. We introduced moment frames and brace frames. Today we're going to introduce what I'm calling the seismic design of buildings. That includes the interrelationships of codes. All of that in preparation for the 4-part design example beginning next week. So, Session 4, Seismic Design of Buildings. We'll address our system of codes. We'll spend a fair amount of time on ASCE 7, the loading document. We'll also talk about diaphragm design requirements, deformation compatibility, very importantly for efficient design, comparing wind and seismic loads. So let's get into our system of codes. Start off here with the local or state code. This is my state code, the 2016 California Building Code. That's based on the International Building Code. So most of our state and local codes simply adopt the International Building Code. Some of them do with slight modifications. Sometimes the modifications only apply to certain occupancies. So we've got a building code represented by the International Building Code. That is going to address what the different types of occupancies are, what's required for plan review and inspection, a number of architectural requirements, but not generally a lot of structural requirements. Most of the structural requirements are in ASCE 7. So here I'm showing ASCE 716. The one that's currently adopted by the 2016 California Building Code is ASCE 710. We'll be discussing both ASCE 716 and ASCE 710, both in this session and in the later examples, to make sure that you understand what's coming down the road in the next edition of ASCE 7, although the current building codes throughout the country generally use ASCE 710 at this point. So, ASCE 7 addresses loads, including seismic loads, certain analysis requirements, and limits on seismic systems, where you can use which system. ASCE 7 and the IBC both adopt the material standards. So if you want to be very strict about it, the IBC adopts ASCE 7 not including where ASCE 7 adopts the material standard. So Chapter 14 of ASCE 7 adopts the steel specification, ACI 318, etc. The IBC doesn't adopt Chapter 14 of ASCE 7, but goes ahead and adopts the AISE specification and ACI 318, etc. So it comes really to the same thing. So this is the 2016 edition of the specification for structural steel buildings and the corresponding manual underneath. Those are adopted, as I said, by will be adopted by the next edition of the International Building Code. They are adopted by ASCE 7 2016. Also adopted by ASCE 7 is the seismic provisions. The seismic manual for the 2016 edition of the seismic provisions isn't out yet, but it'll be this color. I attempted to give it, and the provisions themselves are out and published in this color. So our specification for structural steel buildings and our rules for seismic design are adopted by the IBC and by ASCE 7. Those documents also adopt ACI 318, which we need for some aspects of the design, as we'll see in the design example. So AISE 360, the specification, here I'm showing the manual, but talking about the specification, addresses materials used for structural steel, the strengths of members and connections. There are also some analysis requirements related to design for stability, and those have to be combined or at least considered along with the ASCE 7 requirements. The seismic provisions adopt by reference the AWS D1.1 structural welding code. So some of the rules for welding are contained in that AWS document. The AISE 360, the specification, also adopts the seismic provisions, AISE 341. So in case it isn't clear, sometimes I will refer to these documents by their number. The specification is AISE 360, and the seismic provisions is AISE 341. So 341, the seismic provisions, addresses proportioning, detailing, further restrictions on materials that can be used, and further requirements for analysis for determining the required strengths of elements. So those are the themes that we've talked about earlier with respect to ductile design of steel, and in particular with respect to the design of ductile moment frames and braced frames. AISE 341 also adopts for special and intermediate moment frames the pre-qualified connection standard, or giving its number, AISE 358. So that is a standard that is specifically related to pre-qualified moment connections, which we went over a couple of weeks ago. So these are not the only moment connections that can be used, but these are the connections that are pre-qualified within a certain range, and therefore are very attractive to use for special and intermediate moment frames. The AISE 341 also adopts the seismic welding supplement to AWS D1.1, which is AWS D1.8. So when you have a seismic system that requires you to follow AISE 341, you will have to follow the welding rules in AWS D1.8 that address certain toughness and other requirements related to the welds of the seismic load resisting system only. All right, so let's start with ASCE 7. We'll discuss the underlying concepts, some of the fundamental requirements, the methods used, including determination of seismic design category, selection of seismic systems, handling of irregularity, and determination of seismic base shear, selection of analysis method, and diaphragm requirements. First, let's start with what we're trying to do. What are the underlying concepts with the ASCE 7 method? So the earthquake demand that we're designing for is the so-called risk-targeted maximum considered earthquake. So MCE stands for maximum considered earthquake. Used to be maximum credible earthquake. Now it's just maximum considered. And the subscript R is risk targeted. So previous editions of the ASCE 7 used MCE, and now there's a risk adjustment factor, which sometimes is close to 1, sometimes it's a little bit less than 1, or perhaps even a little bit greater than 1. But it's not taking us too far from the MCE. This return period, generally the maximum considered earthquake in a lot of the country, has a return period of just under 2,500 years. Because of the rules around determination of the maximum accelerations that we design for, in a lot of the western part of the country, near San Francisco, Los Angeles, Seattle, etc., the return period can be a lot shorter, more in the neighborhood of 500 to 700 years rather than, or maybe 1,000 years, rather than 2,500 years. So we're not designing for a uniform hazard. We are designing, though, for an acceptable probability of collapse. Now, the definition of the MCE sub R is, given this level of ground motion, given this earthquake, there should not be a greater than 10% chance of collapse for something designed according to the rules of the code. So it's a sort of joint probability of the earthquake happening and the effect on the structure that gives us the reliability that we're after. So if we just put it in terms of this earthquake, given that this earthquake happens, we want no more than a 10% chance of collapse. So how do we arrive at this level of shaking? Well, this level of shaking has to be such that the probability of achieving, or the probability of reaching this level of shaking, combined with the probability of collapsing under this level of shaking, should produce no more than a 1% chance of earthquake-induced collapse in a 50-year period. So in some areas of the country, this means, because earthquakes are more rare, that we design essentially for a different return period based on the rarity of the earthquake. So more of our reliability comes from the likelihood that this earthquake won't happen during the lifetime of the structure, and relatively less of the reliability comes from the resistance of the structure to that level of shaking. But jointly, those two probabilities come together so that, at least on paper, there's no more than a 1% chance of earthquake-induced collapse in a 50-year period. And that gives us the design forces. There are a lot of approximations in the methods, and I wouldn't say that truly our codes are calibrated to a 1% chance of earthquake-induced collapse in a 50-year period. But on paper, that's how the mathematics, the probabilities are treated in order to get our design base shears for each of the systems. Okay, so we have this very rare event, the maximum considered earthquake, and adjusted for risk. We also adjust it for the local soil conditions. So soft soils tend to move more than stiff soils, and that will have an effect on how the ground motion is communicated to the building. So there are factors that tend to be larger for softer soil to adjust for the soil conditions. We also multiply the spectrum by a factor of 2/3, and then we divide by this R factor and multiply by I sub E, the importance factor, or we divide by the ratio of R to I sub E. So what does it mean to multiply the spectrum by 2/3? What's the point of doing that? The way that I would have you understand that 2/3 factor is essentially permitting us to use effectively a larger R factor. So the code committees could have increased all of the R factors by a factor of 1.5, but instead they said, we're taking this MCE motion and multiplying by 2/3. Now that R factor, that response reduction factor R, represents two things. One that we discussed rather a lot, and that is the ductility reduction. By allowing some structural damage, we can design for a lower force as long as we have a ductile system that can still go out to the equivalent displacement. Another component of that R factor is the overstrength. We design for a base shear of 100 kips, let's say, but we would be surprised if we saw significant yielding at 100 kips. We don't expect to see any significant yielding until maybe 150% or more of that design base shear. So that overstrength is reflected in the R factor. Some of the systems have high overstrength, some of the systems have low overstrength, some of the systems have high ductility, some have low ductility, and it's the combination of the two that really gives us the R factor. The importance factor is essentially the opposite or the inverse of ductility. What the importance factor gets for us is it reduces the ductility that is allowed for certain higher risk category structures. So you can allow a medical office building to see a fairly high level of damage in a major seismic event, but the hospital that's across the street from the medical office building, even if it's seeing the same ground motion and on very similar soil, at least as far as design is concerned, it is not permitted to be taken to such a level of ductility. So we might have an importance factor of 1.5. So the ratio of R over I sub E is going to effectively give us a lower R factor for the hospital, meaning we're going to tolerate less damage for the hospital. So that brings us to the topic of risk category. Risk category is sometimes in former editions of the code, risk category was discussed as seismic use group. It was discussed as occupancy. All of these things come together. Risk category is a general term that applies to multiple loads and other considerations, and it tells us about the occupancy of the structure. It tells us the number of people who are at risk, so how many people are in the structure. Might be an assembly building, it might be a building with a lot of occupants. It might be an important structure for post-earthquake response. All of these things push the structure into a higher risk category, meaning that we tolerate less damage in a seismic event. Also pushing us to higher risk categories of danger to the public. So a hazardous facility might put a lot of people at risk even though the actual occupancy of that facility is relatively low. And so the risk category is reflected in importance factors, higher importance factor for higher risk categories, and drift limits, lower drift limits for higher risk categories. Again, reducing the damage that we might expect for the higher risk category structure. So there are 4 risk categories. There's risk category 1, which might be a shed, an unoccupied structure. Risk category 2 might be a house, office building. All of those things fall into, well, risk category 2 is essentially all other structures that aren't defined as 1, 2, or 3. Risk category 3, assembly buildings, large arenas and stadiums are going to fall into risk category 3. Risk category 4 could be the hospital or other emergency response center, or the extremely hazardous facility might also have to be designed as risk category 4. So here's the table that tells us about risk categories. As you can see, risk category 2 is that catch-all, all structures except those that are in 1, 2, and 3. And risk category 1 is fairly innocuous, but still all of the requirements apply to risk category 2 seem to apply to risk category 1 as far as seismic design is concerned. So here are the importance factors that go along with those risk categories. These are the seismic importance factors. So risk category 1 and 2 get an importance factor of 1, and then we increase to 1.25 and 1.5 for the higher risk category structures. And then this is the basic drift limit. There are other drift limits that apply for specific conditions, but the general drift limit for typical structures is as follows: a drift limit of 2% H for risk categories 1 and 2, lower drift limit for occupancy category 3 or risk category 3, and even lower for risk category 4. Right. Using the ASCE 7 method, we construct a seismic response spectrum, as we discussed. The code gives us a method of constructing a generalized spectrum from maps. There are maps of 0.2 second period, 1 second period, and this T sub L. And they can help us produce a spectrum that looks more or less like this. So at 0.2 seconds, the response at that level creates or defines a plateau to the spectrum. At 1 second, that gives us the information we need for this equation here, which is a function of 1 over period. And then this T sub L gives us both the transition to this other equation, which is a function of 1 over T squared, or 1 over the period squared, multiplied by T sub L. So with all that information, we can construct this generalized spectrum. The values of the 1 second period response and the 1 second period response in T sub L have been mapped by USGS based on stiff soil rock conditions, and they are adjusted by factors for other soil conditions. USGS maps appear in ASCE 7, include peak ground acceleration, 0.2 seconds, 1 second, and T sub L. You can see that in some areas of the country, such as where I am, these contours are very close together and be very hard to design using a printed map. So instead of a printed map, or in addition to a printed map, USGS provides this data online. You can see the web link there that worked as recently as last week. But certainly, if they occasionally change the location, and you can always look up USGS design maps, and you'll find you'll either find this version of the web tool or its successor. We'll show how to use this in the design example. It has all the same data, but you can drill down and get the exact value at your site by either putting in the address or using latitude and longitude as an entry here. You also specify the code and your soil type, and you get a spectrum. Latitude and longitude you can pull up from multiple sources. Here it is from Google Maps for a local coffee shop. We'll have a discussion later whether a coffee shop is an essential facility. It usually is in the morning, but maybe less so for night school. All right, so if you go to the USGS website and enter in your data, it will give you a response spectrum for MC sub R, and it will give you the modification based on the soil type you've entered, and it will also multiply by 2/3 and give you this so-called design response spectrum. You still have to deal with the R factor to get your design base shear and determine what your period is. So let's talk about that for just a moment. Here is the MC sub R response spectrum. As I said, the underlying concept is that we expect our building to have no more than a 10% chance of collapse if this level of shaking occurs. Then we multiply that by 2/3. We don't have an explicit expectation of performance at this 2/3 of MC response. When we don't actually design any member for forces that correspond to this so-called design response spectrum. Before we design anything, we take those forces and we reduce by the R factor. So R divided by I sub E, I should say. And that gives us this, the design forces that we actually design to. So we're designing at a very reduced level, The idea is that we're providing performance at this higher level using the concepts of ductile design and considering the ductility factor and the overstrength factor as combined as represented by the R factor. And this 2/3 MC is a step in between. So remember, our performance expectation relates to the MC, and we're designing for something much, much lower than the MC. Right. ASCE 7 tells us we need to achieve a certain design base shear strength. So that's the 2/3 MC, and then we're modifying it by R over I sub E. And of course, there's that defines the spectrum, and we have to determine our period to see where we are along that spectrum. That 2/3 factor is, again, equivalent to using an R factor that's 50% greater. The R factors that we do have in the code were originally targeted to life safety for a 475-year return period event. We kept the same R factors even when we went to a 2475-year event. And so that's what justifies taking something that's effectively an R factor multiplied by 1.5. As I said, we didn't actually change the R factors. We just left them where they were and used the 2/3 factor to essentially represent the difference between performance that would get us life safety and performance that gets us collapse prevention. And the R factors are system specific and represent ductility and in part overstrength. So here are the R factors for different steel systems. The most ductile ones get an R of 8. Special concentrically braced frames, well, some of that R of 6 is due to a pretty high overstrength. And then the cantilevered column systems, they tend to have very low overstrength, and that's why their R factors are so low. They also have not the greatest ductility, but they also have pretty low overstrength, so we don't give them a high R factor. So here are the equations that we get from in ASCE 7 based on that short period response, SDS, and that includes the 2/3 factor. The period dependent equation that is based on the 1 second period response, again modified by R over I sub E, and then the very long period beyond T sub L, where we're multiplying essentially this equation by T sub L over T, and we end up with T squared in the denominator. So we need to determine the structural period in order to figure out where we are on that curve. We use approximate methods. There are approximate formulae in ASCE 7 in section 12.821. And those approximate formulae are based partly on empirical results or empirical studies, taking the period of real buildings under as large an acceleration as can feasibly be either obtained or induced. So that gives us periods of real buildings that tend to be somewhat stiffer than periods of modeled buildings in our analysis software. They include the effects of cladding and partitions and other things. Here's the approximate period equation. The approximate period T sub A is a function of C sub T, the height of the structure, and this exponent x. The C sub T and x are different for different systems. So you can see that other systems, such as a concrete shear wall, tend to be very stiff, whereas a moment frame could be fairly flexible compared to that shear wall system. So the approximate period is a function of the height of the structure and the system used. As I said, that approximate period will be a lot shorter than what you get out of your model. So if you read something out of your model, it may be a bit more flexible than you can really rely on. Also, if your model is more flexible than the real structure, your required base shear strength may be lower than what you should be using. For this reason, the code imposes a maximum period to be used for the strength check. There's a mysterious K I noticed earlier. You can strike that from your notes. And that maximum period that can be used is Cu times T sub A. So T sub A is the approximate period that we just showed on the previous slide. Cu is a factor, and that's also somewhat empirically derived. So if you are in a place with a pretty high seismic design spectrum, your Cu might be 1.4. If you're a place with a much lower seismic demand, your Cu might be higher, which means buildings are expected to be stiffer in San Francisco than in, say, Las Vegas. And in Las Vegas, they're expected to be stiffer than in Phoenix. So the greater your seismic demand, the stiffer your period is likely to be. And that's represented by this maximum period that you can use to compute the base shear, Cu times T sub A. So if you don't do any building modeling, you use T sub A. If you do use building modeling, you can use the period from your model, but limited to CUTA. You can't use anything larger than CUTA. And we'll show how to do that in the design example. In addition to the required base shear strength, there is there's a required stiffness. That is to say, there's a drift limit, which effectively is a required stiffness. This helps reduce damage and prevent instability. And we're using, say, this spectrum, again, reduced by R over I sub E, but multiplying it by this factor C sub D to get us to expected drift, and removing the importance factor. So when you multiply everything out, the spectrum that we're using for this drift check is 2/3 of MCE multiplied by the ratio of C sub D over R. C sub D over R theoretically should be 1.0, but we're using a lot of C sub Ds over R that are less than 1.0. There's perhaps not a lot of great justification for that, but it does reflect traditional design practice, and it does get us drifts that correspond to the drift limits in the code. So it would seem, in one sense, pointless to change the C sub Ds and then also change the drift limits so that we're doing exactly the same design. So we've left things as is. So this is the ratio of C sub D over R for different systems. For systems that are close to elastic, we use C sub D over R of 1. For some systems, we use a lot less than that, such as eccentrically braced frames. May not be a great reason for that. But this is currently what we have. So we start with, say, at the short period, we start with the short period acceleration corresponding to the MCE, modified by soil type, multiplied by 2/3 to get us to the so-called design level. Then we divide by R over I sub E to give us our design base shear. And for displacements, we get rid of the I factor and put in the C sub D factor. And so it ends up being a function of the spectrum, C sub D over R, and the stiffness of the structure. Similar equations here, just looking at the 1-second period response and the period-dependent response with the factor dividing by T there. All right, there are some proportioning requirements even in ASCE 7. Critical elements are required to be designed for an amplified load. That's using the overstrength factor omega sub O. So we have this defined E sub M, which is a part of a seismic load, which is omega sub O times the earthquake load effect. That omega sub O varies by system. It can be as low as 2 or as high as 3. I guess it's not that much of a range. And so we end up designing for this spectrum, 2/3 times MC divided by R over I sub E, and then multiplied by omega sub O. Elements that we design for that include collectors, and very importantly, elements supporting discontinuous frames and walls. And there are other triggers for this within AISC 341 seismic provisions. So here's a force displacement relationship for say, a frame or a building. We're designing the fuses for forces at this level, and then that would be the braces, say in a braced frame. And then critical elements we're designing for this level so that they don't fail when at the maximum loads that happen in the structure. Importantly, those are, say, columns, and perhaps just slightly less importantly, collector beams, but we design them for the same load combination. There are integrity requirements. Everything with mass has a force requirement associated with it. And everything has to be able to deform in order to achieve the seismic drift. So we don't want the seismic drift to result in, say, a loss of gravity support. There's also an overall stability requirement that limits the second order effect so that we don't have a structure that becomes unstable. We perform that second order check, and we can provide for extra capacity by essentially over-designing our frames. Here's the equation that we have in ASCE 7 in this section. We have P times delta times I sub E divided by V times the height divided by C sub D. So what's the importance factor doing there? Well, the importance factor is actually in the shear. So we're getting it out of that equation. So we're getting rid of the importance factor that's built into that shear. What's C sub D doing there? Well, C sub D is in our drift, so we're actually correcting our drift, getting it down to the elastic level. So really what we have here is P divided by H compared to V divided by delta elastic. And V divided by delta elastic is just essentially the story stiffness of the structure. So we're looking at this P delta effect, P divided by H, that's a negative stiffness, comparing it to the story stiffness that we have. So it's all done very much at the elastic level. And the maximum is this 0.5 divided by beta divided by C sub D. C sub D is here because if the system does have a lot of inelastic drift as represented by a high C sub D factor, we want to make sure the second order effect isn't that great. And beta is the ratio of our shear demand to our shear capacity. So that beta factor, if we're way over designed in our frame, that beta factor can be low, and that means the maximum theta that we can tolerate can be high. There is a cap of 25% or 0.25 for theta max. So we calculate theta and compare it to theta max. There's also a requirement for redundancy. Generally, we want redundant systems. That's a row of one. We get there by having multiple elements that are well distributed. If we don't have those well distributed elements, we end up with a row factor of 1.3, and we get our reliability through that overstrength. So if we have few elements, poor distribution, or high torsion, we're going to design with a row of 1.3. There are two different ways to check if you have perimeter bracing, 2 or more frames. There's a prescriptive allowance that qualifies for a row of 1. If you don't meet that, you can remove one member at a time and check torsion and strength and see if you've reduced your strength or increased your torsion too much. And if you haven't, you qualify for a row of 1, and we'll show that in the design example. Direction of loading. Remember that seismic ground motions are 3-dimensional. They certainly operate in both plan dimensions at the same time. Since those horizontal forces can happen at any angle, it's not enough to take a building like this and just analyze in the X and Y direction and leave it at that. This skewed moment frame that I'm showing here, we have to consider what's the right design case for that skewed moment frame. So you can do another check. You can do the X and Y axes for loading of this building, and then do another one for this one on the 45-degree aligned with that moment frame. That would take care of it. Or you could take the results of your X and Y analyses and combine them either 100% in one direction and 30% to the other, and vice versa, or the square root of the sum of the squares of those forces. Now, If you're taking either of these approaches, 100% and 30% or the square root of the sum of the squares, you are effectively creating something larger than the base shear. So for square root of the sum of the squares, that might be 140% of the base shear. That means that anything that's collecting all of the base shear, for example, if you were collecting all of the base shear in a foundation system and using all of your piles to resist it, you should reduce that back down to 100% of your design base shear, not this orthogonal combination. This orthogonal combination is just a way to get out of applying the load in every direction, one analysis at a time. So it's just a construct. It doesn't mean that you're taking the full base shear required strength in both directions at the same time. Also, often in braced frames, we have, and sometimes in moment frames, we have columns that are shared by two different frames that are not in the same plane. And so we have to consider an orthogonal combination to get the right required strength for this column. And the rules for that vary for each system. So the more highly ductile systems will have higher requirements for this column, and the less ductile systems have less stringent requirements for this column. Talk a little bit about seismic design category. So it's based on risk category, site seismicity, and includes soil effects. So here's a table for SDS, another table for SD1. We take the seismic design category based on each of these tables and take the worst. And then there's a requirement if S sub 1 is greater than 0.75, that could kick us into the higher seismic design categories E and F, E or F. Seismic design category affects the systems that are permitted, the height limits, design requirements, analysis requirements, and irregularity penalties. For seismic design category A, there's no seismic design. We just have the basic integrity requirements of ASCE 7. Seismic design category B, we actually do a seismic design. We compute a seismic base shear. When we select our systems, there are some limits on cantilevered column systems. There are a lot of limits on non-steel systems. As we move on to seismic design category C, we keep all of those limitations and we add more limitations on non-steel systems. We amplify our collector forces. We require geotechnical investigation. We require consideration of bidirectional ground motion. And there are some foundation design requirements. Moving on to D, keep all of those requirements, step up the geotechnical investigation requirements, some further restrictions on system types, including height limits. Some irregularities are not permitted, and there are different penalties, and we have to consider redundancy starting in seismic design category D. There are also vertical forces on cantilevers, some special design of columns shared by intersecting frames, limitations on analysis type, consideration of deformation compatibility, and some foundation design requirements. Okay. Seismic design categories E and F, you have to look out for fault rupture locations, and certain irregularities are not permitted. So here's the table of restrictions with by different seismic design categories. There are height limits. There's a footnote here that says you can go up to 240 feet if you have regular buildings. You can look at that in the code on your own. There's R equals 3 allowed in seismic design categories B and C. There you're just designing according to ASCE 360 using those design equations, QA, QC requirements, and analysis requirements. But there are further requirements in ASCE 7, including consideration of overstrength for at least seismic design category C. For the higher R systems and the cantilevered column systems, we have all those requirements, but you're forced to look at ASCE 341 and design according to those requirements. There are general requirements for columns and connections. And then there are system-specific requirements for proportioning and detailing each of the systems, and we'll go into a couple of those in detail. And then there are some extensive QA and QC requirements. Irregularities, there are horizontal irregularities and vertical irregularities. Because this session is jam-packed, we're going to delay discussion of irregularities until the next session, session 5, and hopefully it's clearer when we actually do the irregularity checks on a building design. All right, there are different methods of analysis that are covered in ASCE 7, modal response spectrum analysis, equivalent lateral force, and response history analysis. The equivalent lateral force is really our base system of analysis. We compute our base shear, and then there's a pretty simple equation that we use to distribute that force. For a very stiff building, a short period, that looks very much like an inverted triangle if the mass is uniformly distributed. This does tend to capture the story shear that we want to design for. It does tend to capture the overturning moment that we want to design for. But it doesn't really capture those forces at the lower levels because of that force distribution. So we have a supplemental diaphragm design force that we also look at. The modal response spectrum analysis is scaled to the equivalent lateral force procedure base shear. In 2010, the scaling factor is 85%. In 2016, that scaling factor is 100%. The code committees have long assumed that the modal response spectrum analysis has some sort of benefit in terms of better proportioning. Hasn't really been borne out in any reliability study, and that's one of the reasons that 85% was increased to 100%. Regardless of that, there tends to be far less overturning for the modal response spectrum analysis forces compared to the ELF forces, so there can be some economy there. The modes are combined using, say, the square root of the sum of the squares or the complete quadratic combination. In either case, we're losing the signs. Static consistency is lost. And any quantity of interest, such as drift, has to be tracked mode by mode and combined. So if you want to know the drift at between the second and the third floor, you can't take the maximum drift at the third floor and subtract out the maximum drift at the second floor. That works for the ELF, but it doesn't work for the modal response spectrum analysis. Instead, you have to track that drift mode by mode and do a modal combination. Response history analysis can be done with linear analysis. You have to get those response histories. That's a bunch of ground motions. You have to scale them appropriately, and that includes, if you're using linear methods, reducing the required strength by R and so on. If you're doing nonlinear analysis, you need to get those ground motions and scale them appropriately and adjust them by soil factors, but you also need to set up your nonlinear model to represent how the building will behave. So you need to get, address how it will deform. The drifts that you get from a nonlinear analysis will be larger than those code drifts for some of the reasons I've discussed, and so the drift limits are allowed to be adjusted. For response history analysis, you have deformation-controlled elements that are modeled with nonlinear elements, and you have to calibrate those to tests or other sources. And then you have force-controlled elements that are modeled as linear and designed according to rules from the steel specification or ACI 318, etc. Okay, if you also have to consider multiple ground motions because buildings do tend to behave a little differently in each ground motion. If you use 3 to 6 ground motion pairs being 2 horizontal directions, not talking about the vertical direction at the moment, you can use the maximum response from all of those. If you use 7 or more ground motions, the code allows you to use the average or mean value. ASCE 7 pushes that up to 11 ground motions for most structures, but for seismic isolation and engineered damp systems, they kept the 7 ground motions. They didn't feel the need to increase the number, and so we end up with a set of requirements that aren't quite the same for some nonlinear analyses and others. So for the technologies of isolation and damp structures, the rules haven't changed, but for other things using nonlinear analysis, the rules have changed. And so here's a table. I borrowed this from Kim Robinson, just a flow chart of different permitted methods of analysis. So here's the information. If you're in seismic design category B or C, you can use any analysis method, no restrictions. D, E, and F, if you're light frame, or risk category 1 and 2, 2 stories or less. Or if you're in a building, or if you have a building 160 feet or less without certain irregularities, you can use any of the methods. If you're in a taller building or have a taller building without any irregularities, and your period is less than 3.5 T sub S, you can use any of the methods. So T sub S is where the plateau of the spectrum turns into this period-dependent part, and so 3.5 T sub S can be way out there. Okay. In other cases, the equivalent lateral force analysis procedure is not allowed. That includes seismic design category D, E, and F. If the building is less than 60 feet and has one of these irregularities, torsional irregularity, soft story, weight or vertical geometric irregularity, or if it's taller than 160 feet and has any irregularity, or if its period is way long, you can't use the equivalent lateral force procedure. Especially for these taller buildings, the higher modes become more important, and the equivalent lateral force procedure doesn't really address the higher modes. And so it's kind of it's not the right procedure anyway, regardless of whether it gives you conservative or unconservative results. It really doesn't represent the building behavior. All right, let's talk about diaphragms a little bit. These horizontal systems, they include gravity supporting members, the deck and the beams. They deliver the horizontal forces to the frames, so they kind of act like beams between frames. Very importantly, they brace the columns for stability. The gravity columns, if you're designing with an unbraced length of the story height, that means something is happening at every story to brace that column. And part of what's happening is the diaphragm is there, so the column can lean on the diaphragm, and the diaphragm can lean on the braced frames or moment frames. The diaphragms also serve to transfer forces between frames, whether it's to overcome changes in stiffness, or whether it's as things yield or fail. A diaphragm provides redundancy by permitting forces to transfer from frame to frame. And as the building goes out to larger drift, there's P delta thrust that the diaphragm resists and transfers to the frames. The vertical distribution of force is insufficient. Here's the ELF. Here are the diaphragm forces. If you look at the equivalent lateral force procedure, as I said, it gets you, the shear that we want to design the frame for. It gets you the overturning moment that maybe we want to design the frame for. But it doesn't give us a lot of force at these lower levels. And if you just design the members at those levels for the forces corresponding to the ELF distribution, you'll end up with things that are going to fail there because the forces will be larger. So that's where the diaphragm force comes in. There's this equation. There's a minimum and a maximum. For the high R systems, this minimum does tend to govern quite a lot. And that gives us sufficient force. Now, if you designed as if each of these forces was acting at the same time, you're going to accumulate way too much shear and way too much overturning. That's not the intent of these diaphragm forces. These diaphragm forces are meant essentially to be applied one at a time. So here are the building design forces that you use to design the frame. Here are the diaphragm forces at each level. Now there's also a requirement to design the diaphragms for transfer forces. These may be 0 or close to 0, but for some structures, especially dual systems and structures with very complex layouts, there can be a lot of transfer forces going from one frame to the other going through that diaphragm. So what we do for those structures is we do an analysis that looks like this, where we consider the diaphragm force at one level combined with the say the ELF forces at all the levels above. And the ELF forces considered at the levels above are only there for the transfer forces. If those forces just remain in the frames where they were distributed to and go down, they won't affect the diaphragm at all. But if they transfer back and forth from a shear wall to a moment frame, you'll be capturing that and adding that to what's going on with the F sub P diaphragm force. That brings us to collectors. Collectors are members that are required to resist axial force, and because they're part of the floor system, they also resist flexural forces. The compressive strength, well, we're designing them for the omega sub O loads. Typically, these are wide flange members with discrete bracing of the bottom flange. If it's just exactly as shown here, without anything on top, without any deck, this member could buckle in the major axis flexural buckling. It could buckle in the minor axis, or it could buckle in a torsional mode. Generally, the minor axis unbraced length and the torsional unbraced length are going to be the same. They may not be, but generally they are. If they are the same, you can ignore torsional buckling because minor axis flexural buckling always gives you a lower strength than torsional buckling for the same unbraced length for a wide flange member. This is a fairly typical condition where we have a composite deck on top of that member. We still could have major axis flexural buckling. We can't really have minor axis flexural buckling because that top flange can't move laterally, and that's not really torsional buckling. It's something we call constrained axis flexural-torsional buckling, and I'll show you what I mean here. Minor axis buckling, both flanges move laterally. Can't have that with the deck on top. Torsional buckling, both flanges move laterally but in opposite directions. Can't really have that with the composite deck on top. Instead, what we have is the bottom flange might move laterally and the top flange is essentially restrained by that deck. So there are equations that we use for that. There's a derivation of that shown in the Seismic Design Manual. We calculate the strength with respect to this buckling mode. And you can see all of these section properties in there, the unbraced length L, and then this dimension A. And that dimension is just the dimension from the centroid of the section to where that restraint is, and we take that as half the depth of the beam, essentially, assuming the restraint is right at the top flange. So the compressive strength, you can also, if you really want to squeeze every ounce of strength out of this, you can calculate the torsional restraint that's provided by the deck and consider also the flexibility of the web, but that's a fairly involved calculation and maybe doesn't get you that much extra strength. But our conservative methods are to design as follows. If you have a steel deck, consider whether the ribs are parallel to the beam or perpendicular. You always have to consider major axis flexural buckling strength. You can always consider major axis flexural buckling strength and minor axis flexural buckling strength. You can always just consider these two as long as your torsional buckling length is no greater than your minor axis flexural buckling length. But there are a couple of cases where you can't actually buckle in this minor axis mode. That includes where the deck is perpendicular to the beam and where you have a composite deck. You simply can't move that top flange. However, I will say that torsional buckling, always less than minor axis buckling if they have the same unbraced length. So for horizontal diaphragms, if you have torsional bracing at each of those points and lateral bracing, you can always just use the lateral, the minor axis unbraced length. And for these two cases, if you don't feel like doing the constrained axis flexural torsional buckling, if you have that, you can always approximate that by using the minor axis flexural buckling strength. The constrained axis flexural buckling strength is always going to be greater than the minor axis flexural buckling strength. So a lot of engineers just ignore this mode and use the minor axis to represent it. Flexural strength, we could have a composite deck. So we use the composite strength in that case. We have a steel deck, could brace us, or we could have a steel deck with flutes parallel, and a lot of engineers just consider that unbraced between lateral brace points. We have collector connections that we have to worry about. There are shear forces as well as horizontal forces due to seismic. Shear forces because it's a gravity beam, and horizontal forces because it's a collector. Those are amplified forces, omega sub O times E sub H. And we still have to maintain, follow the rules that we have for all of our shear connections. We have to be able to accommodate the lateral drift and rotate as required for gravity loads. So all of our simple shear connections in the manual give us 3% rotation capacity. We would like to keep that also for connections we use in the seismic system. For here I'm showing a single plate connection. We might have vertical forces and horizontal forces. All of these different limit states to consider: plate yield and rupture, bolt shear, bearing and splitting, block shear, weld rupture. And we'll go through one by one. In our design example, we'll get to a collector connection and go through all of those. So there's the vertical force, the horizontal force. In the seismic design manual, we convert that into a diagonal force and compute the angle and design the connection for that. What we do in this course, we'll show you later on in session 6, we compute the vertical shear strength and the horizontal strength and simply follow the square root of the sum of the squares interaction formula. Or I should say this is an elliptical interaction formula where we take the demand capacity ratio for the vertical force, square it, and add the demand capacity ratio for the horizontal force, square it, and make sure that it's less than or equal to 1. So there, as I said, we want a rotation capacity for this connection, both for the gravity load deflection of the beam and for the lateral drift that we might get from seismic. So for a single plate connection, there are rules in the manual that limit the plate thickness or the ratio of the plate thickness to bolt diameter and provide guidance on bolt size and spacing. There are also rules for this double column of bolt configuration. That's the so-called extended plate method. And that provides ductility not entirely through plowing of the bolts through the plate material, but also through flexural yielding of the connecting plate, and there are proportioning rules for that. A lot of engineers will, I'll start here, a lot of engineers will calculate the strength of this for a collector connection. It's good for some and might be good for the ends of the collectors, and then graduate from a single column of bolts to 2 columns of bolts. And then when the forces get too much for 2 columns of bolts, they might go to a welded flange connection. If you weld just the top flange, that's great. It certainly has good rotation capacity. It does introduce some eccentricity into the member for collector forces that should be considered. And you can also graduate either directly or from the welded top flange, you can graduate to the moment connection, welded top and bottom flanges. This will obviously attract some moments. So if you're putting this as a collector in a moment frame, this really should be designed as a moment connection consistent with the design of that moment frame. So I would not put a non-ductile moment connection in with a ductile special moment frame, or at least I would make sure that there was sufficient ductility even if I had 2 different connection types. If you have a braced frame that's also going out to large drifts, you should consider having an appropriate moment connection that can go to those large drifts. So some engineers will just put either a special or an ordinary moment frame type connection for their collectors and follow all of the detailing that that you would do for one of those connections, including dealing with the removal of backing and so on. All right, so now we'll talk a little bit about deformation compatibility, which is a very important concept in seismic design. So here I'm showing kind of roughly a moment frame undergoing large displacements, and look at that, the gravity columns also have the same displacements. So it's important to design our moment frame to be able to go to, say, 2, 3, even 4% drift. Likewise, it's important to detail the rest of the gravity beam and column connections and so on to go to that same drift and still maintain the gravity support. So those drifts affect both the lateral and the gravity system. And our performance goal includes preventing collapse, either local or global collapse, so we don't want to lose a beam to column connection. It doesn't mean that we want to keep every column from yielding. The columns will undergo inelastic deformation as we go to large drifts. Doesn't mean that we keep the connection from seeing any failure, but we want to prevent loss of gravity support. This is single plate connection tested at UC Berkeley out to, I believe, almost or maybe even up to 10% drift. And it performed very well. It's not without damage at that large level of drift, but it's maintaining its integrity. And we wouldn't expect that level of drift demand in our typical designs. So we can consider the story drift angle to be roughly the same as the rotation angle that we need to impose on that connection. So we would simply follow the connection rules in the manual for, in this case, a single plate connection. And that gives us a lot of rotation capacity. 3% minimum within the design range, and a lot further in the MC and still maintaining integrity. So if we follow those proportioning rules for simple connections that appear in the manual, we really don't have to do any further justification to demonstrate that these connections anyway can accommodate the deformation demands of the structure. Where we have very flexible diaphragms, the drift of the frame is not all that's going on. We also have the drift of the diaphragm, and we have to consider the angle that, say, this column near the diaphragm midspan has to undergo. Both the column and the connection have greater demands, and those should be analyzed. Increased rotations and increased P delta thrust. One important aspect of design that sometimes, has led to damage are very stiff elements such as stairs. Stairs, if they're hard connected, they can tend to want to act as braces. They're very stiff, and they can be pretty non-ductile. Also importantly, after the earthquake, this is how people want to get out of the building. They want to use the stairs to get out, so their continued function is necessary. ASCE 7 tells us to design them for extra force, but we also need to detail them to allow the lateral drift to develop without damaging the stair system. So details with slotted holes are often used. We want to make sure that those slotted holes don't bind up and don't compromise the ability of the connections to resist gravity forces. So here's an example of connection that might be used where the stair is tied hard into, in this case, say, the second floor, and then has a detail at the first floor where relative movement is allowed in the stiff direction of the stringer, the stair stringer. So as the earthquake happens and there's a story drift demand at this story, we move back and forth within that slot in the connection, and with the understanding that it is not inconceivable that the forces get larger, the drifts get larger under the MC, and even if you damage that connection, you are not losing the gravity support. And I think that's the optimal condition for the stair, is to be able to deform even beyond the predicted limits and still maintain the integrity of the stair. Often there are joints in our systems, either we're at a property line, or our structure is in addition, or we have a structure that's so large we need thermal separation. And there's a potential for two portions of a structure, or a structure and adjacent structure, to hit each other. So there's a dynamic effect where this impact could occur. That's called pounding. And that can be especially serious at property line locations where perhaps the story height differs from one building to the next, and we're not hitting one diaphragm against another, but we're hitting a diaphragm against a column and perhaps causing instability. So there's reasons to maintain a separation there. Typically within the same building, we consider the possibility that the movement is not synchronized, not in phase, and the periods of the two portions of the structure are not the same, but they're also not completely opposite. So what we do is we take a sort of probabilistic approach and design that separation for the essentially the square root of the sum of the squares of the displacements, and those are the amplified displacements, including C sub d, of the two portions of the structure. And we make sure that we don't get structural damage under that level of relative displacement. Now, it could be that the joint cover is damaged at that level of displacement. That's not a structural safety requirement. That's simply a question of what is acceptable to the owner and essentially to the industry. And generally the industry has designed these joints to have some level of damage under these very large levels of displacements, that is to say the C sub d level displacements. Okay. Now there are some conditions that are more critical than just a joint cover. These high consequence conditions are where you could lose gravity support. You could lose your means of egress, and you have to treat them with extra care. So these get designed for the upper bound displacements corresponding to the MC, not to 2/3 of the MC. So this would be a bridge across a seismic joint, where if there was too much relative movement, you'd lose support. You wouldn't just lose a little joint cover, you'd lose the entire bridge. You'd lose a beam or something significant like that. So where I showed a double column connection in the previous slide, this is a single column connection with a bracket. And here I'm going to show relative displacement in the plane of the slide, but there can also be relative displacement out of the plane of the slide. So for relative displacement in the plane of this slide, we've designed this separation appropriately already for the square root of the sum of the squares. Now we design for one part of the building moving to the left and the other part of the building moving to the right. And the magnitude of that movement is 1.5, which gets rid of the 2/3 factor, cancels the 2/3 factor, so we're talking about MCE. And then multiplied by our displacement multiplied by C sub d over r, which is the same thing as taking an r and C sub d of 1, saying we're not reducing by r, we're not amplifying, we're just taking the straight elastic displacement from that full spectrum, that full MC spectrum, unreduced by r. Or if you want to think of it another way, having C sub d equal to r. When you multiply everything out, all you get is 1.5 times the displacement corresponding to the period. R factor doesn't enter in, and C sub d factor doesn't enter in, nor does the importance factor. So that's how we design these critical conditions to make sure that we don't drop a beam during a major seismic event. Tall frames tend to deform not only laterally but vertically, and so we should consider that drift angle. We can actually measure it in our software or do other things. There's going to be a greater rotational demand near the tops of these bays adjacent to our braced frames. Okay, wind versus seismic. As always, we want to design for the governing case and then check everything else. In many cases, different loads govern for different portions. Light cladding is often wind governed, heavy cladding often seismic governed, despite what the base shear says. So for wind, we could have different base shears depending on the exposed area. We've got more or less a uniform distribution, at least compared to seismic, and a moderate overturning compared to base shear. And there's no particular proportioning requirement. There is a serviceability, often serviceability concern, as well as a strength concern. For seismic, the mass contributes, but also the system. So even though you have the same mass for loading in different directions, you may have different seismic systems, different periods, and therefore different base shears. It's a top-heavy distribution with a high overturning moment compared to the base shear. And there are proportioning requirements that usually apply to the overturning resisting elements as well. And so you can end up with very high overturning forces to design for in the seismic system compared to the wind system that has a similar base shear. There are drift limits and strength requirements and the stability requirement as well. So to figure out the most effective way to design, want to compare the wind base shear with the seismic base shear at strength level. If wind base shear governs, you're not done. You still need to check the story shears at each level. And even if the story shears for wind govern at each level, check the overturning moments, including with the overstrength factor where it applies. If seismic governs, well, you also need to compare the drift limits or the stiffness requirement to meet the drift limits. You should always check to make sure that the system you're using is allowed in the seismic design category. You should always check the wind serviceability. Always check wind on lightly loaded cladding and roof screens and so on. And always check seismic on the heavier elements and seismic stability. All right, so we've walked through the system of codes, looked at ASCE 7 for loads, analysis, requirements, and so on. And we've laid everything out so that next time we can begin with a design example and plan the seismic design. A couple of resources related to ASCE 7, the SEOC Seismic Design Manual, Volume 1, and Finley-Charnley's treatment of ASCE 7 for seismic loads. And with that, we're at question time.
Okay, thank you, Raphael. And we do have a few questions from the audience. If you have any questions, feel free to send those in through the chat, and we'll address as many as possible here. But first, let's do a couple polling questions as we do every week, and see how things are going for the audience. Okay, first question. True or false? ASCE 7 gives loaded analysis requirements. AISC 360 gives element strengths, and AISC 341 gives proportioning and detailing requirements. True or false? Does that statement accurately provide the relationship of those standards? Go ahead and submit your answers. Again, the question is this an accurate statement? ASCE 7 gives loaded analysis requirements, AISC 360 gives element strengths, and AISC 341 gives proportioning and detailing requirements. All right, I'll go ahead and close that poll and skip the results. And overwhelmingly, the audience thought that was true. Raphael, I think they're on to this one.
Yeah, I think it's as true as it can be in such a simplified form, right? I'm I'm sure that the people who said it was false are thinking of some particular aspect there where something else is covered in one of those documents, but that's the basic division of labor between those three documents.
Okay, and then we got one more polling question here. Which of the following requirements are directly functions of risk category? Which of these answers is correct? Design base shear, drift limit, overstrength factor, redundancy factor, seismic design category, all of the above, none of the above, or A, B, and E? Again, which of these requirements listed are directly functions of risk category? Give you a couple more seconds if you want to vote on this one. All right. Let's go ahead and close that poll and skip the results. And about 29% said F, all of the above, and about half of you said A, B, and E were functions of risk category. Raphael?
Yeah, so the answer is A, B, and E. For those of you who said all of the above, we did throw a couple of extra ones in there that don't end up being a result of the... Yes, we did throw in a couple of extra ones there. I guess we're a little mean. The overstrength factor is just a function of the system that you've selected, and the redundancy factor is related to the distribution of lateral elements. Neither of those is tied to the risk category.
Okay. All right, let's try to get some questions answered with the time left. I'm going to go to slide 40 for our first question. The question is, when and where in the code is it listed that T must be computed in lieu of defaulting to the use of T sub A for design?
Okay, so that's a good question. To be clear, you can use T sub A for design. You do not have to compute. You do not have to use a model to determine a T, but you are allowed to. And generally, it is if you have a longer period structure where you may come outside of that plateau of the spectrum, as we'll see here on slide 38, then it is advantageous to have the longer period reflected in a lower design base shear. So you're not required, but it is generally advantageous.
Okay. Next question. Are below grade levels considered in seismic mass?
That's a complicated equation, or that's a complicated question, and the answer, the technical answer is sometimes people consider them. So the code is purposely vague and says that the engineer essentially is responsible for determining where the base of the structure is. So if you can take an approach where the base of the structure is down at the bottom of a basement and you include the mass of the levels above, or you can take an approach where you're taking the base shear out at the ground level regardless of the presence of the basement, and not adding the mass of that subterranean of those subterranean levels to the base shear that you're taking out.
Okay. Here's a question regarding light structures. For a light structure in the seismic design category D, E, or F, if wind load controls the lateral design over seismic, do we still need to use special systems and check the seismic provisions?
So good question, a very important point. So if you're in seismic design category, let's say D, you are limited in the seismic systems that you can use, even if wind governs. So you could have a very light structure with very low demand capacity ratios for seismic, but you're still not allowed to use certain systems for the seismic system. And you're also required to follow the rules, all the other rules for seismic design that kick in at seismic design category D.
Okay. Let's see if we can get to a couple more here. This is a question about the overstrength factor, omega. Why is it in ASCE 7, when using the overstrength factor in member design, the code allows using a 20% increase in strength capacity for ASD, but not for LRFD?
Yeah, that is a holdover from older code requirements, and I think it does end up allowing some things to in ASD, or allowing things to be designed for a slightly lower force in ASD than in LRFD. So there's only historical reasons why that 20% is there for ASD, and it really is not right in terms of equivalency and getting the same design, LRFD and ASD.
Okay. All right. Well, we're going to wrap things up at this point.